Good day, everyone. This project is a numerical method solver that allows user to find the roots of mathematical functions using a range of iterative algorithms. It's designed to help students, educators, and technical users apply root finding techniques to real equations without relying on symbolic algebra or calculators. By entering a function and selecting a method, users can observe how differently numerical approaches work towards the same goal, solving equations accurately and efficiently. As its core, this tool helps identify where a given function equals 0, known as its root. Using step-by-step approximation methods, a root is any value of x where the function crosses the x-axis. Instead of solving algebraically, this application uses numerical techniques like interval halving, interpolation, or derivative-based predictions to locate those crossing points. So, to begin, the user inputs a function using Python-style syntax. So, here, you put the function or the equation, and you can set an interval where a root might exist. Then, here you can select the methods, the graphical, incremental, bisection, postposition, Newton-Raphson, and secant method. Each algorithm follows a different strategy to zero in on the solution. Some gradually narrow the search range, while others use tangent lines or secant lines to jump closer to the root. So for example, we will use a graphical method and the bisection method to run the root finding. Once executed, you can see down here the incremental search root detection summary. And here is the function plot with detected roots of incremental search. And the graphical method root detection summary and the function plot with detected roots of graphical method. So, incremental search takes too long to find the root because of the detailed table. So here, as you can see. So here, let me walk you through to the code of my graphical method and how it finds the roots. So in this line, it generates a set of evenly spaced x values across the interval. And the next here, it evaluates the function at each x value to get corresponding y values. So now you can have many and function of x points. So in this line, it loops through its pair of adjacent points to check for sign changes. And so in this line, this checks if the function values at two adjacent points have opposite signs, positive or negative. And the root approximates the root is the midpoint between the two x values where the sign change occurred. And the roots append here, this stores the estimated root. And in this line, it additionally, if a point itself is very close to 0, so in this line, additionally, if a point itself is very close to 0, it's treated as a root. So in this line, additionally, if a point itself is very close to 0, it's treated as a root. So the second condition ensures it's not a duplicated of the last detected root. So, and that's how the graphical method finds its root. So let's go to the bisection method. So in this line, you define the initial interval AB where the root is believed to exist, and this line, it is a k condition if function of A and function of B have the name sign. No root is guaranteed in that interval, so the method returns nothing. So in this while loop, the loop continues as long as the interval is wide enough to. So in this while loop, the loop continues as long as the interval is wide enough and the max number of iterations hasn't been reached. And here, the midpoint C is calculated. This is the new guess for the root. And here, the function values at A, B, and C are calculated to evaluate signs. In this line, if the function value at C is very close to 0, it's treated as a root and saved. So in this line, if the sign changes between A and C, the root must be in that left half, so B is updated to C. So if the root must be in the right half, so A is updated to C. And this line, the current iterations data is recorded and the loop continues. And that's how the bisection method find the roots. And so let's go through the incremental method or incremental search. This line, this initialize the interval A, B, and empty list to store roots, a table of steps rows, and a loop counter. So while loop, for every small step dx, it calculates the function value at the current point A and the next point A plus dx. And the delta x equals dx sets up some metadata for logging. So let's move in this line. So if the sign of function of x changes between A and A plus dx, there must be a root between them. So the root is estimated as the midpoint of this small interval. This line, this avoids saving duplicates roots that are too close together by checking spacing. And this, it records the current step and moves forward by dx. So that is how the incremental search find its root. So let's move on to the Newton-Raphson method. In this line, or in this code, this sets up the list to store its iterations result. The method requires both function of x and its derivative function prime of x. And here, at each iteration, it calculates function of x, the function value at the current guess x0, the function of x, the derivative value at x0. So if the function of x is equals to 0, break. If the derivative is 0, the method stops. Division by 0 would occur. So this acts as a safety check. And here, this is the Newton-Raphson updated rule. So x1 equals x0 minus function of x0 over function prime of x0. This calculates the approximate relative error between the current and previous guess. So this line logs this iteration data guess function value, derivative, new guess, and error. So if AA is not none and EA is, if the error is within the desired tolerance, this method returns the root and the iteration log. Otherwise, the new guess becomes the starting point for the next iteration. Return x1 if rows else none. So after completing the loop or at early stopping, returns the latest root and full log. And that's how the Newton-Raphson find its root. So let's move on to the regular false method or false position method. So this line, first it checks if function of A and function of B have opposite signs. If not, there is no guaranteed root between them, so the method stops early. And in this line, this begins the iteration loop and prevents division by 0. And here, this is the regular false formula. It calculates the function value at the estimated root. So in here, computes the approximate relative error to check convergence. And this row that append is, this stores the current iterations data for the table view, including values of A, B, C, function of x, and error. So in here, if the function value is close enough to 0 or the error is small, C is accepted as a root and the method exists. So next is this. This chooses the subinterval where the sign change still exists and keeping the root bracketed. And here, updates previous values for the next iteration. And when it's done, the iterations are finding a root, it returns the result and log. So that's how the regular false or false position method find its root. And let's move on to the last but not the least, the secant method. So the secant method, in this line, it initializes the method with two initial guesses, the x0 and x1, and prepares a list to store iterations result. For I in range, it calculates the function values at both points. So if function of x1 minus function of x0 equals 0, break, prevents division by 0. The method can't proceed. And here, this is the secant formula to solve the equation. And this computes the approximate relative error used to check convergence. And here, it stores iteration data including function values, new guess, and error. So if EA is not none and EA is less than 2, then return x2 in the rows. If the error is within the tolerance, the method considers the root found and returns it. So here, updates the guesses for the next iteration. The last two values become the new starting points. And when it's done, it returns the last approximation, the full iteration history. And that's all for the 6. And that's all about the 6. And moving on, the software calculates and returns root estimates step by step, iteration data, and error values to show how its method progresses. These results allow users to compare methods side by side, seeing which converge faster, which are more accurate, and where they may struggle based on the shape of the function. This hands-on approach offers both practical insight and deeper understanding into the mechanics of numerical root finding. In conclusion, this numerical method software bridges the gap between theory and application by making root finding algorithms tangible and testable. Whether you're studying numerical analysis or solving real-world equations, it provides a reliable and interactive way to understand how different methods behave. With its accuracy, flexibility, and focus on learning, this tool empowers users not just to find answers, but to understand the process behind reaching them. So, I hope you learned something from this video. Thank you.